Well, why don't we get started? So, hey, everybody, welcome to the 2020 Rosomoff lecture. And it's an incredible honor for me to introduce Dr. Daniel Yoshor as our 20th lecturer in this series, which is really one of the preeminent lectureships at the University of Miami Department of Neurosurgery. I am going to share some slides with you here. But first of all, introducing Dr. Yoshor, who's the professor and chairman of neurosurgery at the University of Pennsylvania. I want to pay due homage to our prior lecturers, as seen here, as well as to Dr. Hubert and Renee Rosomoff and their family for sponsoring and endowing this lectureship for the last 20 years. We greatly appreciate it, and it's really an honor to have Leah with us to help move this lectureship forward. Leah, thank you so much for all you've done for us.
It's a real pleasure and honor, and it's exciting to see it carry on, especially with the demands of the times.
Absolutely. Thank you again. A couple of words about our honored speaker today, who I've known for probably about 15 to 20 years. He's not only a colleague, he's a mentor and a friend. Dan did his undergrad at Yeshiva University in New York, and then did his med school at the University of Chicago. He did his residency at Baylor, and he did a fellowship at UCSF in epilepsy surgery, and then started his academic career at Baylor, and ascended the ranks rapidly, and became chairman of neurosurgery at Baylor probably about 6 or 7 years ago. And most recently, when I say recent, I mean maybe 3 months or so ago, transferred to Philadelphia to become the chairman at UPenn. Not only is he the chairman there, he's also the vice president of clinical integration and innovation at Penn, which is also a very prestigious job at the institution, overseeing at a high level some of the specialties. Being a chairman at two places there's probably only a handful of people who have done that, including Dr. Rosomoff, who is chair at both Einstein and University of Miami. He's had an incredible career, both clinically, but also from a research perspective. And he's really a model of how you keep working at something for a long, long time. And then if you're lucky and good, you can get it into a clinical trial. And that's what we're going to be hearing about today. He's had continuous NIH funding since 2004. He's had articles in Nature Neuroscience, Nature Medicine, Neuron, Journal of Neuroscience, PNAS, and Cell, all of the preeminent high impact journals that we look up to. And again, like I said, he has all of these accolades and is super impressive, but his wife Shira is equally impressive, or maybe even more impressive. And it's great to know the Yoshor family over these years. So I am going to turn the mic over to Dan, but before I do, this is unfortunately is a virtual lectureship, and we really want to do this in person. And I've promised Dan that he's going to work today for a couple of hours, but in a few months, hopefully we'll have him back here just to hang out with us and party with us, and that's a promise. But we do have a lot of formality with this lectureship, an honorarium and a plaque, and through modern technology. I want to give Dr. Yoshor our Rosomoff plaque for his participation today. Thank you again, Dan. Really appreciate it.
Wow, that's amazing. I don't know how you did that. Thank you very much. This is truly a high honor for me. As I will point out in the course of my lecture, it's not only a pleasure to be amongst respected colleagues, but to be amongst people I really consider true and dear friends. So this is special for me, only made a bit bitter by the fact that I can't be there in person. I was really looking forward to spending time. I'm going to start sharing my screen if that's all right.
Perfect, Doctor. Go ahead.
Okay, let's do it. So as I give this talk, I will talk a bit about science, but in the theme of a research day at a major academic program, and that's my slide. Am I doing it right? I don't know if you guys can see me, but I want to pay homage to the U.
Yes, you are.
It's important to me to share some thoughts about mentorship, how mentors have played a role in my career, and how I try to pass that forward, and how much I've learned both being mentored and being a mentor. So let me go ahead and begin my presentation. Thank you.
Reports to bridge.
This is Enterprise.
Captain, I'm switching on the transmitter.
Extraordinary. Yordi, what's that? Over to the left.
What?
Yes, that. No, back. Yes, that, right there. What is that?
That's Commander Riker.
So that was my cold opening and demonstrating what a cortical visual prosthetic will look like in the 24th century as envisioned by the long-running television show Star Trek: The Next Generation. And what I want to do today in the scientific part of my talk is discuss the next generation of visual prosthetics, because the field is entering a bit of a renaissance right now, and there's a new generation coming on board right now. And that will be the theme of my talk today. Just briefly, a couple of disclosures. I have a number of federal grants, and importantly, I have done some work with a company called Second Sight Medical Products, a good, honest company that is trying to advance the field. I am a site PI for a clinical trial that's funded by the National Institutes of Health. I have no financial interest in this company whatsoever. I do not even serve as a consultant. I do have high respect for the people in this company and the good work that they do. I really like this picture. This is a really beautiful picture of Dr. Hubert Rosomoff performing a percutaneous cordotomy, a procedure that he was very famous for, a procedure that required great skill, technical skill, great high stakes, and required a great understanding of anatomy and physiology. And I think it's really very nice tribute that for 20 years you've honored this important leader in neurosurgery and program builder. As Alan mentioned, the chair at 2 programs. He was the youngest chair ever at Albert Einstein College of Medicine, which is the medical school of Yeshiva University, my alma mater, and he served there for 8 years, from 1966 to 1974, before coming over, 1971, 5 years, and then came over to the University of Miami, where his work, of course, is legendary. I will add one other small connection I have with Dr. Rosomoff. His mother was from Philadelphia, and he attended the University of Pennsylvania as an undergraduate, where he received a bachelor's degree in chemistry. So again, I want to repeat, this is a particularly high honor for me. I also want to acknowledge the tremendous accomplishments and legacies in the Department of Neurosurgery at the University of Miami. This is a department that everyone around the country holds in the highest esteem. This is a place where good, honest clinical work of high complexity is done with serious appraisals and publications. And of course, the previous leadership is renowned the world over, Dr. Green and Dr. Hiros. There are many wonderful people currently in the department. I've had the pleasure of knowing some of them. I know Ron, of course, from when he was at MD Anderson. I know Rick from brain tumor circles, and I've been very impressed with Bobby Stark, who I've heard speak at some of the NIH workshops. And I tried to recruit this outstanding young surgeon to Houston when I was there, and I failed. So once again, Alan, you one-up me. Of course, there's tremendous connections I have on a very deeply personal level to the Department of Neurological Surgery at the University of Miami in the present days. I mean, Mike Wang, a wonderful personal friend, an outstanding trainer of residents that I've trained who have gone on to do fellowships with him. Jacques Marcos, a luminary in the field, the cousin of my mentor and therefore my cousin, an incredible leader, an incredible surgeon, an incredible person. And of course, Alan Levy, amazing guy. And it's of course, absurdly falsely modest for him to call me a mentor. The absolute opposite is the case. And I've many times called on Alan for advice and counsel. And he's a person, ever since I first met him when he was teaching the Goodman course, and I was a student, he still is my teacher, and I take pride in that. And I've had the pleasure through the Society of University of Surgeons of getting to know these three folks in a deeply personal way. I would say they resonate, another big three in Miami. And I think it's nice to say that this big three has a lot more staying power, and there are a lot more championships in the future for these three leaders. And I would be remiss if I didn't add Roberto Suazo, who I've also gotten to know through the son, who's a wonderful person. And you all are fortunate to have him and his technical wizardry and his just do everything personality in your department. So I like this quote from the late Justice Thurgood Marshall. None of us got where we are solely by pulling ourselves up by our bootstraps. We got here because somebody, a parent, a teacher, an Ivy League crony, or a few nuns bent down and helped us pick up our boots. And since this is a resident research day lecture, I think it's important for me to indulge in a few minutes about my personal history and how mentors have been so important in my career. And I'm very grateful to the mentors I've had. I'm going to list three in particular, and I think each exemplify an important element that shaped me as a scientist, as a surgeon, and most importantly, as a person. First is Robert Grossman, Bob Grossman, who was the chair of neurosurgery during my residency at Baylor. And Dr. Grossman famously was gentle and kind and operated with a light touch. He liked to say in the operating room always, less is more. And that is how he wielded his power. He spoke softly, and he showed that often being gentle and kind is the true sign of a powerful leader. John Mansell was my research mentor, and in the theme of lessons that I want to pass on, things that helped me develop in my career, I was fortunate and wise to choose the most rigorous PhD scientists probably there is in the neuroscience community, a Howard Hughes investigator and a person who is renowned for just doing the highest quality work. I'm the only clinician that he ever trained in his monkey lab, and he taught me about the importance of rigor. It's not important necessarily to have flashy results. It's not important necessarily to produce the most papers, but you want to produce the highest quality work. And John Mansell really personifies that. And last, I want to talk about my dear friend and truest mentor. This is, of course, Jacques Marcos's cousin that I alluded to earlier. And this is Ray Sawaya, the chair of neurosurgery at MD Anderson in Baylor, who mentored me very closely throughout my career as a young and mid-career attending. He taught me how to be a modern, effective, generous leader, to develop a culture, to build faculty and programs, particularly research programs, and to delegate freely, and to recognize that a leader's primary mission is to focus on everyone else ahead of himself. And I'm very grateful to Ray. I also want to acknowledge the important role that institutions have had in my development. I had 20 years on faculty at Baylor, nearly 6 as chair, and did my residency training previously. I spent 26 years of my life. That's more than half of my life at Baylor. And I'm very proud of what we built there as chair. When I started, we were 25th in the nation in NIH funding. And then just 5 years later, we were 3rd in the nation, and we had a fabulous team, and that department will continue to thrive. And I have tremendous pride in its current status and its future accomplishments. As Alan mentioned, I've been at Penn now for about 100 days. And it's been eye-opening and exhilarating and exciting. And the main reasons I came to Penn were really for 2 reasons: the opportunities to work with a terrific department set in a large system. And these are 3 of our academic hospitals. This is Pennsylvania Hospital, the nation's oldest hospital, founded in 1751 by, among others, Benjamin Franklin. This is the current building of the Hospital of the University of Pennsylvania. And this here is our level 1 trauma center, Presbyterian Hospital. These are 3 of our large community hospitals spread across Pennsylvania, Chester County, Lancaster County, and this one is in New Jersey. This is Princeton University Medical Center, and this is a wonderful system that I think has a lot of opportunities for neurosurgery and for healthcare in general, if we can integrate and leverage the academic developments and innovations into this system in a meaningful way. And that's a challenge I'm excited to embrace. And the last thing I'll show about Penn, this is right across the street from my office, right outside my window. This is the magnificent new building under construction, the new hospital of the University of Pennsylvania, 2 football fields long, and this is going to be the home of neurosurgery, and it's scheduled to open 1 year from now. So now I want to talk a little bit about science. Most of the work I'm going to talk about today is covered in detail in this paper that we published in Cell in May of 2020, just a few months ago. And what I want to do today, and I think one important lesson I've learned over the years that I'll share with the residents, is you don't want to make your talks too complicated. My goal is not to dazzle you or bore you with detail. My goal is to tell a story about my personal journey and about how the work evolved. And I hope that you will walk away from this understanding a little bit about my field. And any good talk should be structured in a way that an educated but non-expert layperson can understand the talk. And that is my goal today. So when I entered neurosurgery, as Alan mentioned, I did a fellowship at UCSF with Mitch Berger and John Mansell at a time when brain mapping was the rage. This was 1999, 2000, and it was really being utilized in the operating room. And I saw an opportunity to utilize it not just in the operating room for brain tumor and epilepsy patients, but also to understand how the brain works. And I was motivated by a curious interest in how the brain works. And that's another lesson I would share with the residents is when you do research, you should pick something you're passionate about. Don't just use it as a means to an end to get the next job, to get the next grant. That never sustains itself in the long run. You have to pick something you're really interested in. And I was very interested in how activity in the brain underlies visual perception. And for the first 10 years or so of my work as a PI, that's what I focused on. An example is this paper that I'm rather proud of that we published in Nature Neuroscience that showed that the temporal parietal junction activity in this particular part of the brain is critical for serving as a gateway that brings visual percepts from the eyes into conscious awareness. If the TPJ is not activated, even though the image is transmitted through the visual pathways, it doesn't enter conscious awareness. Is that something that's going to cure patients? Probably not. Is it important? I believe it is, and it adds to our understanding of the brain. But another neuroscientist, this man here, Brian Wendell, a mentor of mine, who's the chair of the Neuroscience Center at Stanford for many years, he encouraged me to explore an area that had been ignored in abeyance for about 15, 20 years, and that is the idea of using the latent ability of the visual brain to restore vision to the blind. And it's kind of funny that it took a basic scientist PhD to tell a clinician, to tell me, stop just doing theoretical research and try to help patients. And I give Brian credit for pushing me in that direction and launching me into an interesting area of investigation. So let me describe the rationale for a visual cortical prosthetic. What does that mean? Why do we talk about it? So of course, everyone here knows that incurable blindness disables millions of people across the world. In most cases of acquired blindness, and notice I say acquired, if the patient had vision for any period of childhood, the visual cortex is developed and functions. But when the eyes are irreparably damaged, that working visual brain sits there relatively latent and unused. It is used when people think of visual images. If you take a blind patient and you put them in an fMRI and you ask them to imagine a visual image, that part of the brain will be activated, but it's obviously not being used to process inputs from the retina, because the retina, the eye, the optic nerves, whatever the case, whatever the cause of blindness, is broken. And the idea of a visual prosthesis in the visual cortex is to put the information from the visual world directly into the brain, bypassing the irreparably broken eyes. And obviously this is a very attractive idea. The creators of Star Trek, for example, were very well aware of this concept. Now, what is the science that underlies conceptually a visual cortical prosthetic? It really goes back to Penfield, who, when he would do epilepsy surgery in Montreal, and yes, Dr. Levy, I'm sure, tells you all the time, a lot of neurosurgery did start in Canada, that is true. When Dr. Penfield would stimulate the back of the brain, the occipital region of the brain, patients would report seeing a spot of light in the contralateral visual field. And these spots of light, artificially produced through artificial activation of the visual brain, are called phosphenes. They're usually described as a little glimmer, a little flash, corresponding to the map of visual cortex. So phosphenes are easily produced by unnaturally activating the visual cortex. The other point that's critical to the development of a visual cortical prosthetic is it's not random, the organization of visual cortex. And all of you as educated neurosurgeons and neurosurgeons in training know this. There's a very detailed, very precise retinotopic organization or map corresponding to the retina in visual cortex. So it's more than just the left visual world is mapped out in the right hemicortex in the occipital lobe, but that map is very precise and organized in a very, very, very predictable way. So when you combine these two concepts, the fact that you can produce phosphenes by stimulating visual cortex, and that those phosphenes correspond to a very precise and predictable map, the very attractive idea comes to everyone's mind. If you can make one phosphene in a particular spot, why not make hundreds or thousands or millions of them and use them to create an image like pixels on a screen? And this is an image of Jonas Salk, produced with imaginary collections of phosphenes in the spirit of the times. I hope we will have a vaccine to celebrate Dr. Salk in the near future. So what would a visual cortical prosthetic device look like? You would have a patient would wear glasses that are built in with a camera, just for the visual appearance of the glasses. Obviously, the eyes are not working. The built-in camera would capture images from the visual world, and there'd be some pre-processing circuitry to convert the raw signals captured by the camera into a pattern of electrical stimulation that would then be applied to cortex using a device, a collection of electrodes, an array of electrodes implanted in the visual part of the brain. People have tried this, and some of the early attempts are really quite impressive. Here's an attempt that was done in England by the brilliant engineers Brindley and Lewin. As you can see here, in the past, technology was a major limitation. The subject could not walk around with this device because the electrical circuits filled an entire large room. But even in 1968, they were actually able to make patients see phosphenes using this basic concept. Another attempt, widely publicized, and I wonder if Dr. Green and Dr. Hiros remember this, was the neuroengineer and colorful, self-promoting man of media, Bill Dobell, who was based at Columbia University. Bill Dobell invented a more modern iteration of a visual cortical prosthetic. And here you see the patient actually was able to walk around with the device. And he actually published a paper in Nature and a series of other papers, clearly demonstrating that patients could see phosphenes, but not much else. They could see some spots. There were a lot of technological limits. And at most, he showed proof of concept that patients could see a number of spots, but he was never able to get patients clearly in a provable, verifiable way to demonstrate that they could perceive visual forms. And that's, of course, the goal, is not just to see a few random dots across the visual world. We want them to see forms that allow them to guide visual behaviors. Still, progress was enough that the NIH sponsored a major effort in the late 80s and early 90s that resulted in a paper by Schmidt et al. In 1996. And in this iteration, they used small penetrating microelectrodes, and this enabled stimulation with lower currents, much safer for the brain. But these electrodes just did not last. They did not work. There were some complications. And this study was aborted in the one patient they implanted just after a few months. And the study was terminated due to a lack of efficacy and a lack of safety. So in the 90s, this field basically went dark. And that's why I call this talk Visual Prosthetics, the Next Generation, because we really are in a new generation. There's suddenly a renaissance. For about 20 years, there was nothing going on in this field. And I think the reason for this renaissance is obvious, is technology has just changed enormously. The technology, the processing power in this iPhone that I'm holding up in my hand was unimaginable 30 years ago. So prompted by technology, there are now several groups working on developing a visual cortical prosthetic to test in human subjects. One group is in Australia. One group is based in Chicago and funded by the NINDS. There's a very impressive group also in the Netherlands that I've had the pleasure of visiting, funded by the Dutch federal government. And I'm involved heavily in two studies in the United States. One is funded by DARPA, by the Department of Defense, and that's a clinical trial to develop a very ambitious, totally new form of hardware for a visual prosthetic, led by an engineer that I work closely with at Columbia named Ken Shepard. And my arm of the grant, I'm the PI for all the non-human primate and clinical trials that will subsequently occur in human subjects. And this was started at Baylor and will shift over to Penn. And the other study, the one I'll talk about today, is one that's actually underway, and we can actually report on a small number of patients. This one is funded by the National Eye Institute, and this started as a collaboration between Second Sight, the company in California, my colleague Nader Paratian at UCLA, and my group at Baylor, which is now in the process of moving over to Penn. And I'll focus on some of the results from that trial. So what are the problems with the existing visual cortical prosthetics circa 2020? Well, one problem is this is what the Second Sight prosthetic looks like, and it only has 60 electrodes. There are some other designs that are in development that have smaller electrodes, that have a few hundred electrodes, but we have a relatively small number of electrodes, and especially with the penetrating electrodes, it can be very challenging to maintain fidelity, to keep those electrodes going. Let's do a little thought experiment for a minute. So this is what a 5x5 of electrodes might be imagined to produce if we had 25 electrodes, and let's say we had 25 pixels. And I'm going to take you through progressively more electrodes to see how many electrodes we really need to produce. In theory, if everything works perfectly and if the brain processes this information in the most favorable way, let's see what we need to get something useful. So here's 25. This is an 8x8 or 64. And this is roughly what we have with that second site Orion, the one that we've implanted in 6 human patients as part of a FDA approved early feasibility trial. And you can see something, maybe some forms. This is a 100 electrode array, which is equivalent to the Utah microarray that's widely in use in functional neurosurgery labs. This is what 625 electrodes or 25 might look like. And here we're getting into a 40 by 40 or 1600, 50 by 50, 2500, 100 by 100. Here's 10,000 electrodes. And obviously when we get to 40,000 and 250,000 and 1 million, you can see potentially a very high resolution, very precise form. I'm going to emphasize strenuously in this talk that this is not the reality, that phosphenes are not pixels, but this is the theoretical limit of what we could achieve. And you can see it's very tantalizing. This is 1 million pixels. And when I mentioned that DARPA project that I'm working on, that actually is the goal of the DARPA project, is to produce a device with 1 million electrodes, an impressive engineering challenge. It has to be wireless. It has to be instantaneously functional. It is a daunting challenge. And this is sort of the theoretical limit of what we could achieve with 1 million electrodes. So what is our overall approach to building a better cortical prosthesis? We think the approach needs 2 arms. You need to have a hardware approach, and that's where you focus on making more electrodes, better electrodes. But I think it's going to be very important, as I've struggled to advance in this field, we have to understand the neuroscience better, how visual information, how electrical stimulation is processed by cortex. We can't assume that we can dump this information in the brain and it will be instantly perceivable. We have to reinvent how we stimulate the brain by understanding fundamental neuroscience principles. And I like to say that's the software side of what needs to happen. So let me talk a little bit about what we've done in our lab. So early on in our lab, we really focused on the epilepsy patients. We couldn't implant blind patients to test these kind of technologies. So we would take patients who are undergoing implantations for epilepsy. Dr. Jagged and his group, of course, are doing this in Miami and others all around the country all the time. What we would do is, along the edges of the grid, we would for clinical reasons, I was always trained, we would always slide a strip electrode in each direction, north, south, east, west. And the idea of those flanking strip electrodes is, just in case we didn't have the grid placed very well, we would know where we could shift the grid to if our early recordings indicated that we weren't well localized relative to seizure onset. So we took advantage of these flanking strip electrodes, and we developed hybrid research electrodes where we use the space in between the electrodes on these strips for research recordings and stimulation using much smaller research hybrid mini electrodes. And that enabled us to study the brain. So here you see the frontal lobe, here's the temporal lobe, and of course in this direction, going this way, is the occipital lobe. The strip that's slid in the flank at the corner of the occipital lobe, these research electrodes will be in the occipital pole. And we've done this in dozens of patients with absolutely no adverse effects. So there's 2 main ways we could study visual cortex in these patients. One way is to present a visual stimulus on a screen in different locations and see where a specific location in the visual world will activate a specific location in the visual cortex, and that's called receptive field mapping, a classic technique used in studies beginning with Hubel and Wiesel, the Nobel laureates who really did the groundbreaking work on visual cortex in cats decades ago. Another way is going the opposite direction. We can stimulate visual cortex and then have the patient report, draw on an LCD, what their visual percept looked like. And this is a big advantage for us at neurosurgeons. And this is something I want to talk about with the young neurosurgeon scientists who I hope are listening to this talk. As neurosurgeon investigators, we have to take advantage of research where our unique access to the human brain provides a qualitative advantage. The best monkey scientists in the world cannot stimulate a monkey brain and ask the monkey to draw where the stimulus was, describe what the stimulus looked like. There's a level of information we can derive from humans that is unique and very important. So using these kind of techniques and a series of sophisticated psychophysical experiments, we've explored how visual cortex is mapped in human patients and which areas of visual cortex produce phosphenes. So when Penfield did his work, and this is a drawing from Penfield, he had no idea how visual cortex was organized. He knew the occipital lobe was involved in vision. We know today that there are actually not just V1, not just V2, not just V4, not just MT. There are over 30 visual areas in the occipital lobe, in the temporal lobe, in the parietal lobe. It's really amazing. About a third of your brain is dedicated to processing visual information. So which parts of the brain can we use for a visual prosthetic? It's a practical as well as a theoretical question. Can we only use V1 that straddles the calcarine cortex, or can we use other areas? So this is a paper we published in 2009 in PNAS where we did a detailed exploration of different areas in visual cortex, and we demonstrated that V1 and V2 and V3, we can very reliably produce percepts stimulating the brain on every single trial, every single time. Much more difficult in later visual areas, and in the most complex later visual areas in the hierarchy of visual processing areas that are important for producing percepts of complex forms or visual motion, it's actually very difficult to get a visual percept. So the practical lesson is stick to V1, stick to V2, stick to V3 if you want to develop a visual prosthetic that exploits the parts of the brain that reliably elaborate phosphenes when stimulated. Why is it that the later areas of the brain, we know they're visual, why don't they produce phosphenes? I like to say it's kind of like banging on a piano. If you bang on a piano in a very simple part of the brain, you'll produce music, a tone, a harmonious tone. But if you start banging on piano keys in a more complex part of the brain where the organization is much less spatial, but much more informed by form and higher visual percepts, the brain interprets that as a cacophony and does not recognize a percept, and nothing is produced. Now, we've done a fair bit of work in the computational neuroscience realm, and I won't get into the details of these equations, but we've developed mathematical models that are going to be very important for a visual prosthetic. We need to be able to know reliably what we're going to produce when we stimulate a specific spot in the brain. And developing mathematical models based on empiric recordings and stimulation, we can predict very reliably where the phosphene will be and quite reliably what it will look like when we stimulate a particular place in the brain. And you can read about this in our Journal of Neuroscience 2017 article. The big leap that we wanted to take, and this picture is taken from a couple of grants ago, we hope that we could just use phosphenes as voxels, as pixels on a screen like we do every day. And we knew that in our epilepsy patients, we wouldn't have a very high resolution view. We wouldn't have 1 million electrodes, but we would have enough electrodes, 27 electrodes, a 9x3 array in that hybrid grid that I showed you. And we thought that we could use multiple pixels in combination to produce crude letters and numbers, crude graphemes. And our goal, this was a methods figure from an old grant, we would make the patient see the number 7, make the patient see the letter V, make the patient see the letter I, make the patient see the letter L by stimulating in different trials, different patterns of electrodes to produce different groupings of phosphenes. And we thought the brain would do the work and put it all together, and we'd make a big advance in the field. If we had read Dobell's work more carefully, we probably wouldn't have been this naive. Dobell tried to do something like this in 1976, but the best he could do is have the patients see letters using cortical braille. He was never able to stimulate groups of phosphenes to produce the letter A, the letter B, the letter C. What he did is he taught the patients to recognize that different groups of phosphenes are codes to represent different letters. Just like in Braille, different raised bumps on a page represent different letters of the alphabet. This is not seeing forms. This is learning to associate skillfully different patterns of dots with a specific form. It is not vision. It is a code. It is a form of sensory substitution. And when we did this in our patients, this is what we found. I could play this video quickly. In the interest of time, I may jump ahead on some of my videos, but this shows when we would stimulate multiple electrodes at the same time, it was difficult for the patients to integrate that information. And this is nothing like the letter L. They're just seeing discrete spots. Now, one might say if we had a better, tighter pitched array of electrodes, if we had intervening electrodes in between, maybe it would all come together. And that is a possibility, and we've done some experiments to test that. But it's very, very unclear that the brain is going to integrate simultaneous stimulation of multiple phosphenes into viable, recognizable, coherent visual forms. This is the idealized pixelated letter. This is what we want to achieve. More often we get something like this, and sometimes the brain will ignore some blobs and recognize other blobs. So simultaneous stimulation of multiple electrodes in order to produce a coherent percept by assuming the brain will put those phosphenes together like voxels on a screen, in our experience, has not panned out very well at all. And to overcome this, we've adopted some different strategies. So one strategy that's worked very well for us that we tested and highlighted in this recent Cell paper is a strategy we call dynamic current steering. And every medical student knows if you want to test somatosensory function, one way we do it is we draw letters and numbers on the patient's hand, and patients are easily able, when sensory pathways are intact, to detect those letters. But if you pressed simultaneously spots in the palm and try to get them to identify a letter by integrating those spots and try it, we've tried it in people, including ourselves, it's very difficult to do. The brain is highly adapted to detect changes. That's one reason this is a strategic approach. Another reason is we're sweeping across the map and visual cortex, just as we sweep across the receptors, the somatosensory receptors in the hand, and we produce intermediate virtual electrodes in between the physical electrodes. Remember, I told you one of the problems is we don't have an electrode covering every millimeter of the brain currently due to ethical and clinical and technological limitations. We can use current steering not only to sweep across, but also to produce steering of current to points in between the two electrodes. And the goal is, with this technique, is to take this approach, which didn't work in producing a coherent percept, and see if by sweeping across dynamically very quickly, could we engage the detection centers, the perceptual centers of the brain, and produce a coherent percept, even with a relatively small number of electrodes. And here's an example. We take a map of the brain. This is in an epilepsy subject, so this patient is not blind. And remember, the maps on the brain, there are precise maps, but they're not entirely veridical maps. So the Z we draw on the brain to produce a theoretical Z in the visual world is not exactly point-to-point correlated with the map. And I can explain that in detail later. The map is sort of like the somatotopic map that we're all familiar with from Penfield's classic drawings. It's not the hand, the lips are bigger than they should be in proportion. The same exists in visual maps where the fovea is much larger than eccentric areas. And that explains why the dots are not exactly the same. So here our goal was to produce a dynamic activation of cortex to give the subject a percept of a letter. And after several years of failing miserably by doing concurrent simultaneous stimulation of multiple points, you can imagine how excited this was for us when the patients without any training were immediately able, with their eyes blindfolded initially, or they have no idea what we're tracing on their brains. They're actually able to immediately report a very coherent percept of the letter that we predicted and desired to produce. And here's an example for another EMU patients using the limited electrodes we have for reasons that everyone in this room is familiar with. We can't just put an infinite number of electrodes in the brain just because of our research in these epilepsy patients. We were able to derive percepts using dynamic current steering of letters that were remarkably similar. These are the patient's actual drawings, and this is what we predicted. And you can see how similar they were. Then we moved on to blind subjects, which was very exciting and part of our collaboration with Second Sight. And here, just using 5 electrodes in a subject with a crude prototype, we were able to get the patient instantly to, in this case, produce an upside down U. This patient is completely blind. This is a wireless transmitter turning on her electrodes. And you can see here, each color tracing is a different individual trial. And we tried to get what we called, and this is just using 5 electrodes, so it's not nearly as robust in comparison to the percepts we want to produce. But look how reliable these tracings are from trial to trial. And the patient was able to identify letters with excellent accuracy in this fashion. We moved on to the more fully formed prototype of the Second Sight visual cortical prosthetic. And between us and UCLA now, we've implanted 6 subjects. Here's an example of a subject just reporting a series of phosphenes that we're producing on the screen. So he's blind, so he uses his left hand to maintain fixation with his brain. And there he's showing a series of phosphenes that we produce in succession. This man has not seen in, I think in this guy's case, it's 11 years.
Starting now.
I know I'm moving kind of fast. I apologize for that. So this is where the Orion, the 60 electrode array, is implanted. And we're trying to straddle the calcar and cortex right there. And this is a map. Some of the phosphenes are above the in the upper visual field. They're produced by the lower bank of the visual cortex, and some are in the lower visual field. They're from the upper bank of visual cortex. And this is the map of each phosphene produced when each electrode is stimulated individually. And we tested a variety of functions, initially using Second Sight software that mostly does simultaneous stimulation. And this is another one of our subjects in Houston, and he's doing a square. This guy hasn't seen it in almost 30 years. And his job is to use the device to point to where the square is on the screen. No light perception. This is entirely based on what we're inputting to his brain.
Correct.
And you can see it's not easy or intuitive. He's only working with 60 electrodes. There's a training element, and the way we combine the electrodes is rather primitive here. This is not with dynamic current steering. This is the standard Second Sight software. He's mostly using it as a contrast or light detector. Here his job is to find a square on the table. I should have mentioned in the previous slide, we had the device off and he was unable to find the square. He was just guessing. Here he adjusts his camera. Here he's navigating in the halls, and we have a nurse behind him, and believe me, this is far from ready for regular use, but using his detection of variations in contrast, he's able to do some very rudimentary navigation. Here he's pointing, he can see the greater light in the window, he finds the corridor. Very, very crude. We have a long way to go. I really don't want to oversell this.
Definitely see the sun.
This was kind of moving for me. I don't know if you guys could hear. But what he just said there at the end, he said, I definitely can see the sun. And here he points up at where he sees the sun, and you can see the shadow behind him. And again, this gentleman has been blind for many years. This is largely light detection. It is not visual form detection. And what we really want to produce is the ability to see visual forms, even rudimentary visual forms. And I'll skip some more of the Orion data. Now, this is what we have done using the technique of dynamic current steering. The Orion proprietary software that the company developed has not reliably, or forget reliably, they have not tried to test form vision. They're just trying to test the ability to detect large, highly contrasted visual stimuli and maybe use that to navigate a little bit. Here we're using dynamic current steering to try to produce images of letters like I showed you in these sighted subjects. So this isn't a blind subject. You can hear my postdoc Denise Oswald telling him next one. Now we'll stimulate. He's drawing what he sees and saying the letter it corresponds to. We trained him to detect different letters, and he has to be able to tell us what letter it is with high accuracy. And he actually got very, very good at it. He was well over 90% accuracy. And here in this task, we looked at 4 letters. If he's guessing, of course, he'll only get it right 25% of the time. So he was way above, he was 37 out of 40 typically in trials in sets of 10. And you can see these are individual tracings of what he drew every time. And they're really quite reliable from trial to trial. And this is the foundation of our cell paper, is for the first time in the published literature, we're able, using clever backdoor stimulation techniques, specifically dynamic current steering, to greater access perceptual capabilities of visual brain. We're for the first time able to produce at least some rudimentary percepts of a visual form. As I said, we want to improve the hardware and the software. On the hardware side, we're working with our colleagues at Columbia Engineering to develop a flexible array with 1 million electrodes. And here's a surgery I did in a monkey. This is on a macaque, to insert and test a prototype. We're still a long way from implementing this. It's a daunting challenge to produce 1 million electrodes that all function wirelessly and can both record and stimulate. And that's what DARPA does. They fund almost science fiction level projects. But that's the goal in the long run, is to use 1 million electrodes to really harness maximally the capabilities of the brain to interpret and derive percepts from information that's delivered through wireless stimulation, driven in all likelihood by machine learning algorithms over time. And this is what it would look like, a flexible array. And that's the goal. So I apologize that I couldn't be more interactive. Normally when I give a talk like this, I call on the residents a lot and I want to have some back and forth, but this sort of forum across Zoom doesn't really allow for that very easily. So let me conclude with a few points and perhaps take some questions or comments. A new generation of advanced VCPs, visual cortical prosthetics, is emerging, and that's why my talk is called The Next Generation. That is what we're looking at, a next generation. This is a very exciting time in the field when you consider for 20 years there was nothing, and now multiple groups are pursuing it. So far, the only one that's FDA approved and being tested in human subjects is the Orion. And it's been demonstrated thus far to be safe in early feasibility testing. And it does lead to some performance benefits in visually guided behaviors, like I showed you, detecting large contrasted objects and maybe some navigation in a hallway. And that trial was put on hold for a while because of COVID. UCLA and Baylor subjects are about to resume activity this month. I would also emphasize we have a long way to go, and it's not just building a better mousetrap. Understanding the science of brain stimulation and visual perception is critical to the success of these prosthetics now and in the future. I would emphasize phosphenes, those dots that we produce by stimulating the brain. They're not pixels. You can't assume that they're combinatorial elements, that the brain will just put them together the way the pixels on a screen easily coalesce into images in your living rooms. And the last point from our most recent paper, stimulating the brain dynamically can be used to increase the amount of visual information delivered, and specifically to produce some rudimentary percepts of visual forms like letters and numbers. Lastly, I just want to thank the many people involved in this work, my partners in my lab at Baylor and Penn, actually, and Bill and Denise have already moved over to Penn. Mike is joining me at Penn in a couple of months. Ping is going to stay at Houston and work together with Samir Sheth and continue to follow up on our patients there. I want to thank Brett Foster also, who is joining us at Penn from our research group. Samir, a wonderful functional neurosurgeon, brilliant scientist, and a fantastic colleague, is going to do amazing things at Baylor, and his future is incredibly bright. Andreas Talias, Ken Shepard, great scientists at Baylor and Columbia, respectively. Nader Sarish at UCLA, great neurosurgeon, also the brilliant future, brilliant scientist. These are the folks at Second Sight, the EMU doctors, the clinical trials office, and of course the patients. Of course, the funding. We couldn't do it without the funding. And lastly, of course, thank you for your attention. Am I doing it right, Alan? Yeah. Thanks to, oh, there, that's better. Got it. To the you. Thank you very much. And again, I want to thank Leah. I want to thank Alan and the entire department. I want to thank the Rosomoff family. I will display this with great pride, and this really is a high honor for me. And let me have 30 more seconds, Alan, to say, those of you who know me know I'm a straight talker. And so when I say this, I mean it. I think Miami is fantastic. I always have. It's not just because I like these people personally. This is a kind of program that exemplifies a research lesson that I always state, and that is, I love research. I'm passionate about research. I don't think I need to prove that to anyone. I think we can all assume that. I will stand here and say the research mission is hollow if there isn't accompanying clinical, surgical, technical excellence. Being good at research in the lab is not a substitute for taking great, honest, attentive care of patients with a high degree of technical excellence. And the University of Miami exemplifies that with great surgeons and great research. And the Miami Project, of course, exemplifies the concept of taking great research and applying it to patients. So I am humbled to be talking to you. You really should be teaching me. And frankly, you have. So thank you very much.
Dan, that was fantastic. A true highlight of our academic year. And again, thank you for doing this. And again, I promise we will have you here in a few months, hopefully, to break bread and spend some quality time with the residents. We have about a minute or two for questions. So I'll open up the mics for a couple of questions.
Do you want me to unshare my slides at this point? What would be best?
Yeah, unshare your slides. Awesome. And I'll ask you a question. So you showed very nicely how important it was to stimulate V1, V2, V3 in the occipital cortex. That's the best way to do it. The visual axis is long from retina to brain. Do you think there's any other areas that might be plausible to do this?
Excellent question. First of all, I talked about visual cortical prosthetics. There's a whole huge field of retinal prosthetics. And in fact, Second Sight started as a retinal prosthetic company. So if you think about cochlear prosthetics for audition, they don't go for the cortex, they go for the sensory end organ, the cochlear fibers. The problem with retina is it's very, very small. There's cortical magnification occurs. The visual cortex is the size of a credit card. That's V1 alone, by the way. Retina is tiny, flimsy, delicate, and very difficult to implant. People have hypothesized putting electrodes in the lateral geniculate nucleus. People have hypothesized doing it in the optic nerve. Very reasonable targets. The advantage of visual cortex is it's a beautiful map that's very orderly. In the thalamus, it's spread out in a three-dimensional matrix, but these are all viable strategies. And I also want to emphasize on top of that, the patient must have had vision for this strategy to work. You guys know Hubel and Weasel's classic work. If you don't show a baby visual images, God forbid if you did an experiment, they do this on cats, where you sew the cat's eyelids shut, that corresponding visual cortex that corresponds to the retinal inputs from that eye, that visual cortex will not develop if you miss that critical period. And if you try to reinstate visual inputs a year later, it's too late. So it has to be a developed brain. And yes, earlier targets are viable. The other advantage, though, of not doing the retina, going to the brain, is there are a lot of retinal diseases, macular degeneration, RP among them. Those patients, you can't do a retinal prosthetic.
Maybe time for one more question, and then I'll pass it over to Dr. Jagged, to introduce our next speaker. All right, John, take it over. Thank you. Thanks again, Dan. Really appreciate it.
Thank you so much.
So it's my honor to present our next speaker, Dr. Ian Cahigas, currently a chief resident at the University of Miami. I've been, having the honor to work alongside him over the last 3 to 4 years. He obtained a PhD from MIT in electrical and biomedical engineering, and then went on to Harvard Medical School. He has a particular interest in neuronal signal processing and brain-machine interfaces. He's been working over the last 3 years on a unique BMI paradigm to restore hand function in spinal cord injured subject, and will be starting a functional fellowship at UCSF this coming June. He'll be talking to us today about a unique continuous signal processing paradigm for brain-machine interface, allowing for easier in-home use of the technology. Ian?
Thank you, Dr. Jagged, for the kind introduction, and thank you to Dr. Yoshor for an amazing lecture, very inspiring to see all the things you've been able to accomplish to finally give patients that are blind the opportunity to see again, and hopefully some of this work in 20, 30 years will have similar implications to helping patients regain upper extremity and lower extremity function after spinal cord injury. I first want to start off saying that this is a project that has many people, and I'll present the work. It's clearly not just my work. This is the work of many students and PIs that have been sort of driving this technology forward. So what is a brain-machine interface? Dr. Yoshor showed one example, but in general, the definition is it's a communication system that doesn't depend on the brain's normal output pathway of the peripheral nerves and muscles. And that's how the term was coined about 20 years ago. More recently, just as in the case we saw with visual prosthetics, brain-machine interfaces can create new pathways for the brain to read out information or to write information into the brain, such as what is done with the visual prosthetics. The origin of the term goes back to UCLA in 1973 with Dr. Jacques Vidal, who basically posited the idea, could these brain electrical signals that we're able to record from EEG be used to control external devices or even computing systems? As we saw, one of the most prominent modern examples of these brain-machine interfaces is the restoration of visual perception in patients that are blind, as Dr. Yoshor discussed. And there have been other recent advances where these brain-machine interfaces have been developed to help patients with spinal cord injury walk again. This is from a group, Alim Benabid in France, their cortical prosthetic for controlling exoskeleton and being able to help the subject ambulate as well as use both upper extremities. In the interest of time, won't go through the whole video. Hopefully some of the same methods that were used in this paper we'll discuss in more detail as we talk about the development of our work here. But they were able to train the subject using these virtual environments, and then find the relationship between the brain signals that are being recorded on the ECOG and how they corresponded to the different types of movements. And eventually they use this external orthotic device controlled by just the subject's brain signals to allow him to move his arm to specific targets, as well as internally, externally rotate the arm and to take steps on a robotic exoskeleton. So, you know, this is a very exciting field to me because, you know, these are sort of where you would start off if you were to say, okay, well, if we were going to take human functions that are lost, you know, can we restore them? But it opens the door to lots of other ideas. And I'll show a few just to show that, you know, this field is just at its very beginning. Eddie Chang at UCSF has recently been using ECOG to decode speech. And one can imagine using ECOG to help patients that are, say, locked in communicate with the world. Here's an example where what they do is from the ECOG decode the actual movement of the mouth, and from the movements of the mouth, they're able to synthesize what the speech would have been.
The proof that you are seeking is unavailable in books.
The
proof that you are seeking is not available in books.
So that was the subject actually speaking, what you heard last, and then you heard the synthesized speech from the inference of how the oropharyngeal muscles are moving based on the ECOG. There are so they've been able to successfully do this decoding of speech from ECOG. And recently in the same lab, Dr. Chang has been working with Mariam Shaneshi, who's an electrical engineer at USC, to develop predictions of mood based on ECOG. So similarly, epilepsy subjects are asked to record their mood while they're hospitalized. And based on ECOG signatures, they could potentially predict how the patient would be feeling. And you can imagine the ramifications of being able to track how somebody is feeling if what you're trying to do is optimize deep brain stimulation for depression or other neuropsychiatric disorders. So there's a lot of examples of this field that has potential to help lots of individuals. In particular, though, here at the Miami Project, we're very fortunate to work with people who are thinking about how to take patients that have suffered a spinal cord injury and really help them regain independence and improve their quality of life. And we have both from the inpatient side, where we work as neurosurgeons, to the large team of rehabilitation doctors that we work with in order to help patients improve after usually trauma or even tumors that cause them to lose the ability to use their arms or legs. Paralysis in general is a big burden to society because it usually affects young individuals and it decreases their ability to contribute to the jobs they used to perform. And on average, a 25-year-old patient who becomes paraplegic will have up to $2.3 million of lifetime medical costs, whereas somebody who's quadriplegic will be anywhere between $3.5 and $4.8 million. So the ability to treat these patients, give them the ability to be independent and contribute to the things that they would love to contribute to and work on will not only help them, but also decrease this cost burden as a society. If you were to discuss with spinal cord injured patients what they would want restored if they had the ability to have any function restored, most patients with quadriplegia uniformly say that they would like hand or arm function restored. And among paraplegics, the ability to ambulate, as well as other important functions such as bowel, bladder control, or sexual function are also important targets. But given the fact that ambulation and arm hand function is important, we sought for this particular project to focus on how we could use brain-machine interface to try to restore some upper extremity function. So there are many, this is by no means not new. Many people have tried using EEG or the microelectrodes with the Utah array which have culminated in a series of very well-known papers by Lee Hochberg and the BrainGate group, John Donahue at Brown, where they've implanted patients with quadriplegia with these microelectrode recording electrodes or Utah arrays in motor cortex, and use that to control things such as a cursor on a screen to allow patients to interact with a computer, and even control external robotic exoskeletons to provide them the ability to feed themselves, basically mimicking hand function. Our particular project focuses on the use of the event-related desynchronizations, which, as Dr. Yoshor mentioned, was originally described by Dr. Penfield. So a lot of the early epilepsy work by Penfield, like elucidating the occurrence of visual phosphenes with occipital lobe stimulation. In this particular case, he noticed that whenever he was near the precentral hand region and the patient was asked to clench their fist or relax their hand, there was an obvious change in the frequency content of the EEG or ECOG that was being recorded from the surface of the brain. So based on this observation, we sought out to do some preclinical work where we asked the question, are these event-related desynchronizations seen in patients who no longer have hand function when they do think about the motor imagery of moving their hand? And the short answer is yes, and that this event-related desynchronization can be reliably picked up and used to trigger functional electrical stimulation of the hand. And so subjects are asked to look at a screen where they're either told to move or rest, similar to Penfield's original paper. And EEG is used to detect the event-related desynchronizations, or the frequency content of the signals that were being recorded, and whether there's any corresponding change as they think about moving their hand or not moving their hand. And so this is an example of a SEI subject and a control subject. In red, you can, in green, you can see that when somebody is not moving their arm and just at rest, there is a peak in the low frequencies between 5 and 15 hertz. It's called the beta band, and that peak in frequency decreases when somebody thinks about movement. And that this is replicated not only in the spinal cord injured subjects, but also in control subjects. This is an example of the experimental paradigm. So here the subject is asked to relax and now think about moving. The ECOG, the EEG is red. The frequency analysis is done, and when it's correctly detected that he thought about moving, then electrical stimulation of the hand was applied. This was robust across subjects. So in this grid here, you can see the row corresponds to a single subject, and the labels at the top just correspond to the different electrodes on the EEG. And so you can see is that at this trigger, when they're asked to move, you can see a decrease in the power in these low frequency areas. So it goes from red in these low frequency bands to more green. And so detecting this transition is sort of indicative that the subject has gone from thinking about rest to thinking about move. And then this was used to trigger stimulation of the upper extremity in these subjects. And this was able to be done with a very good degree of accuracy, approximately 74% across the subjects that were tried for this pilot study. And using this data, it sort of motivated us to try to do something invasive to showing that this is possible, to actually try it on human subjects. At around the same time, Medtronic had released a implant that record ECOG in preparation of their closed loop DBS initiative. So the idea is there had been some evidence that when patients' Parkinsonian symptoms are getting worse, the ECOG in certain areas of the frontal lobe would change, and therefore you could potentially have a device that didn't just always stimulate Parkinsonian patients with deep, electrical stimulation. It would be able to modulate how much to stimulate for how long, depending on the severity of the symptoms as detected from the ECOG that was being read. And that's actually now been released into the market. And in around 2014, they had made this research device available to a bunch of different labs, Miami being one site. And this is an example of a group that used the same device and similar principle with the event-related desynchronization to do typing on a patient with ALS. So the way that this worked is that by reading the ECOG, they could detect whether the patient would think about moving their hand or resting their hand, and the movement of the hand would be used as a virtual computer click. And so the spelling system worked by flashing lights on the rows, and then if a particular letter that the patient was interested in was in that row, they would visualize moving their arm. That would be detected as a click. Then that row would be highlighted, and then the columns would begin to highlight one at a time. And when the patient saw that letter that they wanted to type, they would again think about moving their hand, and that was a virtual mouse click. And so doing this, the patient was able to type in environments where they couldn't before. So for example, a lot of these typing systems for patients that are locked in or have ALS are based on tracking eye movement. So in areas where the light is very, very bright and that the eye can't be tracked robustly, those systems don't work. So this patient was able to use this system for over a year with no change in the ability to decode. So
may I ask one question, please?
Yes.
Sir, in this case, the patient is obliged to have this device throughout his life as long as he or she needs to work with. But that's not like a holistic solution, isn't it? Like in Parkinson's disease cases, patient, they have shaking hand, right? In that case, person, can we apply this one also in that case? Did you get my question?
So I'm not sure I understand. So the question is that the time in the ALS patient, yes, they will have this condition for the rest of their life, and they're going to have to keep this device as an implant. That was the first part of your question. And then I didn't understand the relationship with the Parkinson's.
Okay, sir. Thank you.
Okay,
please carry on.
We can talk about it offline. Yes. All right. And so around this time, with the opportunity to use the Medtronic PC+S, we sought to apply the same paradigm that we had with our non-invasive studies to patients with spinal cord injury using the implanted ability to read the ECOG over the motor cortex. So we screened about 22 subjects, finally encountered one subject who was interested and did well with the screening and interested in pursuing the surgical arm of the study. Again, consisted of the Activa PC+S. The S is what allowed us to do the real-time sensing, and then functional electrical stimulation of the hand that was applied by this device called the BioNess, which basically is an orthosis that the person wears that can apply stimulation to different muscle groups to help with hand grasp. This is a preoperative imaging of the subject. It's showing an area of T2 signal in the center of the cord. At the level of the injury, you can see the prior ACDF that was done at that level. We brought the subject preoperatively for an MRI, not only to look at the fiber tracts and help us identify and plan where we were going to do our craniotomy near the hand area, but also did a functional MRI and asked the subject to visualize moving the proximal arm, the deltoid, which he could move, as well as to visualize moving the hand. And you can see in red near the sort of straddling the hand knob, you can see the red is thinking about movement and the green is actually moving the proximal shoulder. And those overlap. And so we use both of those regions to plan a craniotomy for placement of our electrodes. You can also see also that they correspond to the areas of the descending fiber tract, cortical spinal tract. So this is a surgery in 2018 in November. And so then the setup with the implanted devices as follows. The subdural electrodes are placed over the hand knob and basically are connected to the subclavicular generator. There's a external receiver that reads the ECOG data and transfers it with a USB cable to the computer, and the computer then has access to the real-time ECOG that the subject is producing. The subject is asked to move or rest, same as the paradigm earlier, and when that's detected to be correct, electrical stimulation of the arm is applied. We optimize the configuration of the electrodes to pick up the biggest signal when somebody was thinking about move or rest. And this is what the data looks like. So here you can see the time waveform for a particular channel, channel 1 and channel 3. And you can see that when somebody thinks about moving, that the high frequency activity goes down. We built, this is just some slides to say that we extracted some features based on that frequency content and trained numerous different classifiers to make sure we weren't tricking ourselves into just seeing something that we wanted to see in the data, and showed that we could robustly decode the move versus rest with about 90% accuracy using a range of decoders, and that this ability to decode the move versus rest was stable over all the 21 sessions that we recorded with this subject. So this is an example of the subject in the lab. So again, asked to think about not moving, think about moving the hand. The ECOG is being read, decoded, and then stimulation is being applied to the hand. We got started, the subject is extremely motivated, and he asked us, well, could I actually try to do something with this stimulation? And so we designed initially just a simple task like picking up a cup. And this is him trying to pick up a cup when he receives that stimulation. And so that the device is providing stimulation to open for a certain amount of time, and then close for a certain amount of time, and then open once again. We tested various components of the Jepson-Taylor hand function test to see whether stimulation or training had any improvements in the subject's ability to function over the duration of the study. And we showed that he had some improvement in the ability to lift small and heavy objects, as well as a slight trend towards improvement in the writing. You can see the writing here on the right side, where by the end it's much clearer and faster that he was able to write certain words. We, again, motivated by our subject and his constant wanting to kind of use this in his everyday life, he wanted more challenging tests. So here we designed one where he would have to pick up the object from a target and take it to another target on the other side of the table. It's definitely not perfect. These were the first couple of times where he was attempting this. Again, just like Dr. Yoshor, I don't want to oversell what's possible with this technology. There's still lots of things that need to happen to make this ready for prime time. Here he's able to put it right at the center of the target. Okay. And we were able to quantify how accurately he was able to place the checkers on the center of the target, as well as a small cup, which was what you saw in the video. And we see improvements over the training in his ability to accurately place both of these objects. We also sought to see, just like in the ALS example, could this signal be used to trigger other motor tasks? So maybe initiation of stepping. So we, together with a company that provides one of the exoskeletons in the Miami project, we asked them to modify it to let us use our control signals to actually trigger the stepping. And so here he's thinking about moving his dominant hand, and that triggers the stepping of the exoskeleton. And this was stable. The accuracy was similar to the accuracy of the upper extremity tasks and remained stable over the duration of the sessions that we tested here. They were not quite as accurate. It's a little bit less. And this is, this is because this is a subject who hadn't really been upright in a number of years. And we think that the combination of the being upright and the exertion, as well as having to focus on moving the hand while actually the legs are moving, all those things add a extra cognitive load that might decrease performance slightly while the subject is becoming familiar with the task. We've also been able to integrate this device with the brain machine interface with other devices. So this is a glove, motorized glove that allows the subject to close the fingers. Here, thinking about moving the dominant hand on the right side, but we only had a left-sided glove at this time. So here he's picking up a cup, and when he thinks about rest, the glove opens. And this is a subject who has no hand function. So this is starting to allow him to do things that are way beyond what he's able to do at home. So here he's going to grab it again, bring it to the other side. And what was very interesting to us at the conclusion of this in-lab portion of our study was that the subject, one day just comes up to us and says, "Oh, by the way, I think I can move my finger now, my thumb." And we took a video. And he does have some hand function. Now, we never anticipated such an improvement, and therefore we don't have preoperative EMGs here. Is this natural course of his spinal cord injury, and he would have gotten this improvement regardless? It's unclear, something that we will definitely study in the future. But it does fall in line with a lot of basic science data that when you have stimulation above and below the level of an injury in the nervous system, that somehow promotes plasticity and reinnervation. So we at that point, having concluded the in-lab portion of the study that we originally submitted to the FDA, we started to think, well, can we continuously decode what the subject's thinking about, whether or not we're telling him to think about move or not, because ultimately that's what would be the most useful of an implant like this, that he could just think about moving his hand or not, and that signal would automatically be transformed into movement of an orthosis or functional electrical stimulation. So this is just an example of what the data looks like when he's thinking about move or rest. So the x-axis here is time. What you see in the colors are the different power and the different energy band and frequency bands. And when you see when he's thinking about rest, there's this high frequency component here that goes away when he thinks about move. And so wanted to then use all of the data from the device, from the 4 channels that are implanted. And unlike the visual prosthetics, the things that we have available for for this particular study, we only had 4 channels, which are a total of 8 contacts that were implanted over the hand motor cortex. So not a lot of data. So we were trying to maximize using all 4 channels. 2 of those channels are the power that's computed on board the device, and 2 of those channels are the raw ECOG. And so we sought to build an algorithm that just by observing those 4 channels, we could infer what the subject was thinking about. I won't go through the math, but just to show an example of simulation study where we have the simulated power in different frequency bands, which is this observation, and we have the underlying true state of move or rest, and we developed algorithms that could decode the likelihood of being in one state or the other. And the good thing about these algorithms is that in theory, you could add more states. So it could be maybe right hand move, right hand rest, left hand move, left hand rest. You could continue to expand them. The algorithms do that easily. Our current implementation only allows this move and rest on one side based on the data that we're able to collect. But we were able to use this, the subject was able to use this sort of continuous decoding to control this ping pong game. So thinking about move would move the paddle up, and then thinking about rest would move the paddle down. And so having shown that this was possible, we implemented it with the glove system. And so here, there's no longer a computer involved telling the subject what to think about or not. He's just thinking about move or rest, and we detect it, and then that gets cinematically to the glove. This is the first day he did this, so he has to really focus on rest while the algorithm triggers the rest, and he's able to drop the checker. So since that time, this was early 2019, like April, we've been working on how do we get this stuff in his home environment and out of the lab. You know, the device is fully implanted. Most of the limitations of a lot of the previous devices have been that people have to be plugged into these power supplies, expensive systems in the lab. Here we have the ability uniquely that the device is completely implanted in the patient and we can read the signals across the skin. So the last year and a half is really focused on getting this system in the home environment. And so I was very fortunate to last summer work with Kevin Davis and Charles Oliver, who were both MD PhD students here at the University of Miami. And they were able to put together a Bluetooth app that allowed the subject to control which device was being read, which device was used as an output, in which case he could use his iPhone to select that device in the home setting and trigger it. This is just an example of the video of the app here. Able to pick which input device, so say it was an EEG or it's the built-in ECOG, to calibrate it by doing the rest and move stuff that we were doing in the lab, but it would all be done through the phone. I was also very fortunate to connect back with my former PhD advisor, Dr. Emery Brown, and get him very excited about the potentials of this kind of work. And he put at my disposal very brilliant grad students and master's students to work on implementing that math that I mentioned earlier into a real-time decoder that could be run in Python and integrated with our phone app. And structure the model in such a way that we find the optimal parameters that need to be obtained from the data. And this is just showing how the parameters were selected. And here at the bottom, you can just see that on the right side, you get this home classifier. When we actually tested it in the home environment, had accuracies that match the accuracies that we were getting in the lab, which is reassuring. And this is an example trace of the move and rest and the decoded state. So the dark gray is when the subject is told to move. The decoded state is this black line here. That's when the state is decoded as move. You see there is a short lag of the decoder, and that's based on the inherent sampling periods of the device and the technology that we're currently working with. We've also worked with two undergrads, Shovan Bhatia and Sebastian Gallo, to design a computing system, basically a 3D printed housing for a computer that he could then use in the home environment. So here is actually the subject in the home environment with the system. This is his brother helping him set it up. So basically just has to power on the computer, connect the USB cable that goes to the antenna that reads the signals from the subclavicular generator. And just in the interest of time, I will just advance the video a little bit just to show that here he's positioning the antenna over the device. And putting the glove in the dominant hand. And once this is done, he can control the rest from his phone. So the main assistance that he needs is with setting this system up, connecting the glove. And at this point, potentially for the rest of the day, he could use the device and control it from his phone. So this is the subject now configuring the system using his iPhone. Pairing to the appropriate devices, And again, we're very fortunate to have a subject who loves technology and loves pushing us to do more innovation. So it's a two-way street. Like if we're just very blessed that he is the person that we've been able to work with. So here now he can select the Nexus, which is the actual device. Oh, yep, they're having issues with the devices, so he reloaded it. And he's able to find the device now. And they're connected the phone to the glove. He's able to calibrate the system just like we did in the lab. So you're thinking about rest, thinking about move. And again, we're not intervening. Nobody is intervening here. The subject is doing all of this. Once the system is calibrated, we could then use it to do different tasks. So here he is picking up a brush. It takes a little bit to get it appropriately positioned in his hand. There's lots of opportunities for improving the technology here. The orthosis doesn't relax or extend the fingers. It only flexes the fingers. So he has to use the passive mechanism of either extending his fingers by pushing them down against his chest or pushing them down against the object in order to really open the hand. Fast forwarded here, he's able to grab the brush and brush his beard. And brush his hair. And here, he loves listening to music. Here he is picking up his headphones. We tracked several measures of independence, a spinal cord injury measure and the SF36, and there were some trends and improvements in independence with the use of the glove across the study. And so this is where we are as of today, and I wanted to kind of share some thoughts about where I think we can go with this. So one master's student and an undergrad at the University of Miami have been working on looking at the original data that we got in the lab, and there's an interesting potential to detect rest and move of the dominant hand. But when you think about moving the non-dominant hand, the contralateral side, there's an event-related desynchronization that's not as strong. This has been described previously. One potential explanation is that we do a lot of bimanual tasks. So whenever I think about moving my left hand, there's some part of the right hand motor cortex that's almost preparing to assist the other side. That's just speculation, but regardless, there is a change in the event-related desynchronization. There is an event-related desynchronization that's seen in the dominant motor cortex when you think about moving the non-dominant hand. And we can potentially think about using that to discriminate left hand move versus right hand move, and maybe allow our subject some bimanual tasks where he now has control of both hands with a single implant. The other area where we've been sort of pushing forward is we're limited by the technologies that we have and currently being able to control 1 degree of freedom, which is open or closed. But could we then build easily accessible devices that allow the subject to maximize this open and close to do other things he wants to do, such as feeding himself, opening doors, or picking up a pen. And we've designed in the lab a couple of experiments where the subject is able to pick up these small beans and take them to a target, and also been able to use this latch system to open door. And he's also been able to use that spoon system in order to help with self-feeding. And this just shows the amount of time it used to take him at the beginning. He did improve over time. He was unable to self-feed before any of these devices. So that's why there is no comparison here. And this just shows the accuracy with which he's able to get a small object to his mouth. This is an example of him using the 3D printed system to open a door.
I think you got it.
That was the first time he was able to do that, and he made it look so easy that everybody started laughing. Again, very incredibly lucky to work with our subject. And so, motivated by these initial findings on this patient, we're trying to set up the next generation study. So we've paired up with a company in Germany that develops a fully implanted system that's both able to read and write. It has a total of 64 channels and is powered externally, so there isn't a need to, in the future, change implanted generator. And it's powered inductively across the ear, just like the cochlear implant. So you wear a small thing over the implant that's able to both power it and serve as a way to download the data. And then we've been working with Battelle, who developed this wearable sleeve that can stimulate muscle group, a wide range of hand and arm muscle groups to create more coordinated or complex movements. And we're currently putting together an NIH application to do implants of these systems in the next round of studies. But in parallel, we've been thinking about how spinal cord injury. This is one potential solution, but could other avenues of neuromodulation or stimulation help to improve motor recovery? And I was fortunate to listen in on one grand rounds that Stefano gave several years ago when I was doing my research, and I was like, Stefano, I saw this video, and let me show you the video, and then I'll tell you the conversation that happened. So this is a thoracic injured rat, unable to ambulate on a treadmill. And they begin to apply electrical stimulation of this place called the cuneiform nucleus in the midbrain. And all of a sudden the rat is able to not only begin ambulating again, but actually gets out of the harness and no longer needs the harness to keep him up. And so Dr. Noga, Dr. Guest, Jan Opries are here at the Miami Project. Stefano's doing his MD PhD, his PhD with them. So and I told Stefano, well, we got to figure out a way that we're going to try this in humans with spinal cord injury. And we said, well, that's going to be a long shot with the FDA to put an electrode in the midbrain of somebody with a spinal cord injury. How do you prove safety? And so we then started to think about, oh, here's another video that he showed during the same talk. This is a pig with no spinal cord injury, but showing that you can modulate the speed by changing the frequency of stimulation. So here the pig, turn on the stimulation, the pig now is head is to the front of the treadmill, and you could actually modulate the speed, and if you stimulate on either side, one nucleus or the other, you can even help with turning. So we had that conversation, we said, well, actually, if you look at where this cuneiform is, it's right near the PPN, which has been tried for freezing of gait in Parkinson's disease. And we launched a study, which hopefully implant our first patient by the end of this month, when we're going to aim to stimulate the cuneiform nucleus in patients with freezing of gait to see if they get more significant improvements. And the reassuring thing is that when you look at all several studies that have shown their electrode locations and the outcomes of PPN stimulation. Those electrodes that are closer to this cuneiform nucleus are actually the ones that are associated with patients with better outcomes. So it may be that it's indirect stimulation of the cuneiform nucleus that makes these Parkinson's patients get better. And that's very exciting for us, because if we can show safety and efficacy of that target, then it potentially, with some of the basic science work that they've developed in Dr. Noga's lab, potentially target that for spinal cord injury as well. This is an example of how dramatic a difference stimulation of the PPN can have on patients with Parkinson's disease. This is a patient with severe Parkinson's, can't really walk. You see, almost completely frozen, small steps. Once he initiates, able to take a few steps. And, yeah. And so we'll see here post-operatively. So maybe this stimulation is actually closer to the cuneiform nucleus, at least that's our hypothesis, than the actual PPN, and that subjects will have the benefit from this. And so one can imagine then combining strategies where maybe instead of providing functional electrical stimulation of the hand, you're actually providing neuromodulation to the cuneiform nucleus to drive spinal locomotor circuits to assist with ambulation and maybe help some of our spinal cord injured subjects regain some walking function in the future. So in conclusion, event-related desynchronizations remain present despite chronic spinal cord injury. It can be robustly triggered by visual imagery of movement of the dominant hand. That our fully implanted brain-machine interface can be used to decode hand movements accurately, and that the accuracy remains stable across time and remains stable across the different tasks that were tried, both with walking and arm function. The use of functional electrical stimulation, such as we did, may have the ability to restore volitional hand grasp, as we saw by that interesting observation that the subject's thumb movement improved during the period that he was receiving this functional electrical stimulation in the lab. And that the improvements that we see are also captured in the functional assessments, both in the independence, spinal cord injury independence measures, as well as the functional tasks that the subject was able to perform. And there is a continued improvement in accuracy with use, as we saw in both the self-feeding tasks and the tasks that he performed in the lab. And that a paradigm based on these event-related desynchronizations may hopefully be applied towards restoration of other modalities, such as ambulation, and potentially other degrees of freedom as we begin to understand how other motor tasks are encoded within motor cortex and have the ability to record from a wider area given new devices. So I'd like to conclude just by thanking everybody involved in this project from conception. Dr. Jagged had the foresight to put this project together, and Dr. Abhishek Prasad, who worked with all the students in his lab to make this a reality. The MD PhD students that I've worked with over the last year, and all the master students that have helped kind of integrate the technology together, as well as my former advisor at MIT, Dr. Brown, and grad students that I've been fortunate enough to work with there. I also like to thank the Miami Project for funding the study, as well as NIH for the partial funding for this research year. And I'll conclude with that.
That's a great talk, Ian. As usual, phenomenal work. You've been the primary driver of this project and really have just created amazing sort of innovations as it relates to the project. The only question I have is, do you think that these paradigms that use ECOG, as opposed to, you see these brain gate, right, paradigms where you clearly get, I think, more degrees of freedom and better signals per se. Do you think that this this route of sticking to ECOG will eventually or ultimately be as good?
Yeah, that's a great question. And I think that the primary difficulty with the current microelectrodes has been that you lose neurons over time. And I think that that might change with newer technologies. Maybe that's something that Elon Musk's Neuralink will solve. Or, you know, maybe it has to do with the biomaterials, the density of the electrodes, but ultimately you're right. The microelectrodes give you higher degrees of freedom because you're picking up all this information from individual neurons as opposed to the global population of neurons, which is what you're getting with ECOG. I think ultimately the combination of the two, or the ability to do the combination of both, will allow you to extract more information. Maybe in some tasks, the group neural population code is telling you something about the task, and the individual neurons are telling you something about the nuances within that task. And the ability to fuse the information from both the group level and the single neurons are going to be important. I know that the groups such as Neuralink are looking at ways to use both local field potentials and look at individual neuron firing patterns in order to build their next generation of brain-machine interfaces. And I think that it's going to be by understanding which paradigm is best for what task that we'll be able to determine what's going to be primarily used for particular, and especially as we begin to delve into things like cortical prosthetics for depression or other things. We don't even know where that information lies.
I think this is really, really nice work by you and Jonathan, and I think it's really smart and opportunistic and strategic. You're at the home of the Miami project. This is an incredible opportunity to go beyond just the classic and very important spinal cord injury research that's been pioneered there, with Richard and Mary and for so many years, and Barth, and moving into neurophysiology as a second strategy. I think, or in your case, probably a 10th strategy. It's a busy place. I think one of the interesting things about this field, and it's a very interesting field that I'm more of an observer than a participant, is you talked about the key issues of is this scalable? Do you need more signals? Do you need more precision? It's also interesting, does it really matter that you're in the primary motor area? And Richard Anderson's work, for example, the brain is there's so much going on that we don't really understand, and you can take signals from the parietal lobe, from LIP, you can take frontal lobe signals, areas that we don't classically think of as particularly directly related to encoding motor activity, and get very robust levels of responses. So I would argue, and this is a strategy that I've employed, is absolutely the problems of materials biology and sampling and density of electrodes and fidelity of signals and durability. Those are obviously critically important. But I think as neurosurgeons, what we can really bring to the table is understanding the neuroscience better, the neuroanatomy better, and what signals are relevant and what aren't. I'm not as ambitious. I mean, you have an engineering background, but I don't really get into so much. I collaborate with people. I want more electrodes. I want, just like you do. But I just wonder if we can enhance our understanding just of the cortical signals just in other areas of the brain and see how they can decode information. I think there's a wealth of material there. The question I wanted to ask you is all this stuff that people are doing now with haptics and haptic feedback. Are you embracing that? Because the other thing that's impressive about what you're doing is you're actually doing this in patients, and you have these incredible young, motivated patients who it seems like will try anything. Are you trying to get more immediate practical benefits with a haptics approach at all? Is that something you're thinking about?
Yeah, so the problem with the haptic approach is usually requires being able to stimulate through the electrodes that you're have in order to be able to generate the equivalent force or interaction. There is great evidence in primates that can be done. They can they can feel like they're interacting with virtual environments. We, unfortunately, there is no active technology that we had access to for this study that does that. Now, the next generation device that we're collaborating with has the ability to stim as well.
The device that we're working on through the DARPA project, you're welcome to use it when we make it. I mean, that device in theory, would do the same thing. I mean,
and so yes, absolutely. Or as we're thinking about the next generation of this is, could you straddle both the motor and sensory areas if you had enough space to actually decode the motor intent and take information from the periphery and stimulate and give the sensation of what's being done by the orthosis. And that in theory could help the closed loop sort of performance by the subject. But yeah, at this point, we have no sort of tangible experience with that. We were just proposing to do that using the next generation of devices that will be able to stimulate and record.
And what about this functional improvement you saw related to presumably to motor activation that you mentioned as sort of a byproduct? Is that something you're going to explore systematically?
Yes, so we plan on doing preoperative EMG assessments on all the subjects for the next round of studies, and actually doing like SSEPs to see whether the sensory pathway is intact, as well as doing some subthreshold stimulation from the device once implanted to see whether there is any presence of conduction. So you could get at least a baseline. And in theory, you could build an ongoing assessment of how the motor system adapts by doing this sort of over time. You could basically have your own in vivo MEPs and SSEPs that you're tracking. And so you could get a quantitative assessment of any improvement from your rehab component or from just the neuromodulation that's going on.
Well, that's very, very impressive. And I hope you have a great experience in San Francisco. It was the year I spent there was a very important year in my career. And I think Eddie is terrific, and Phil, and you'll be under their orbit and build on what you've done with Jonathan and the people in Miami. I think it's very promising, and you should acknowledge that R25. Dr. Levy worked hard to bring it to the department. That's an important thing. So acknowledge it more prominently. I encourage you to. Great work, really impressive.
Thank you very much.
Open up the floor to questions. I know there's a question on the chat, if you look at it, Ian, about Dr. Courtine's work.
Chat here. Oh, no, I mean, so Gregoire Courtine, just to summarize for those who aren't familiar. So Gregoire Courtine has done a lot of work. He trained with Reggie Edgerton, is at EPFL. He's done some work using spinal cord injury in monkeys. And one of the most recent papers, they're able to take the cortical signals from the monkeys and stimulate below the level of injury in the spinal cord and help the monkeys walk on a treadmill. Definitely think that this sort of paired both reading of the neural signals above the level of the lesion and neuromodulation below the level of the lesion. I think that's a lot of the future of how we're going to be able to repair spinal cord injury along with the biologics, because you're almost recreating what happens in the utero. You need to have signals above and below certain neuronal targets to help with migration of neurons, creation of new synapses, and then having the right biology and neurochemistry available to facilitate those connections. And so I think that being able to bypass the lesion electrically will allow you to initiate function, but I think it will also help the nervous system guide its repair. So I think that Gregoire Courtine's work is sort of paradigm shifting what we're going to need to do in the future to effectively treat spinal cord injury.
Awesome. Well, it is almost 9 o'clock. I want to thank both Dr. Yoshor and and yourself, Ian, for doing a fantastic job. And also want to thank Dr. Landy, who's integral in developing the program, Ingrid Menendez, Roberto, Ignacio. Again, a very successful Rosomoff visiting professorship, where we'll make it real in a few months, Dan. Thanks for joining us. Appreciate it.
Thank you very much, and congratulations to Ian and to the whole department. Very impressive.